Inequalities with and. Two inequality statements can be joined together so that both inequalities have to be true. These types of inequalities are called compound inequalities. So for example, let's say that x is greater than -3 and x is less than or equal to 2. This is a compound inequality. It's a combination of two inequalities that must each be true. So to solve a compound inequality means we have to find all the values of the variable that make the compound inequality a true statement. So in order to do that, we're going to solve each inequality separately, and we're going to consider the two solutions, which we also call the intersection of the two inequalities. And so you can consider it just like the intersection of two streets. The part where the streets overlap belongs to both streets. And so what we're looking for in our inequalities, or compound inequalities, or what are the values that overlap and satisfy both inequalities? What is the intersection of those inequalities? So we're just going to start with an example. We're going to solve the compound inequality of 6x minus 3 is less than 9 and 2x plus 7 is greater than or equal to 3. So we'll start just with the left-hand inequality. 6x, take away 3, it's less than 9. And to solve this inequality, we'll add 3 to each side. So 6x is less than 12. Then we divide each side by 6. So we know that 6 is less than 12 divided by 6 is 2. So that's one of the two inequalities. And we also know that 2x plus 7 is greater than or equal to 3. So we subtract 7 from each side. So we have 2x is greater than or equal to 3, take away 7 is -4, divide by 2. So x is greater than or equal to -2. So this is a possible way to say our answer. However, it's not the best way that we could say our answer. X is less than 2 and x is greater than or equal to -2. And I'm going to demonstrate that by drawing a number line here with -2, 0, and +2. So over here, we're told that x is less than 2. So that means any value less than 2. And over here on the right, we have that x is greater than or equal to -2, which means that -2 could be included, but that x must be greater than, heading over to the right, greater than -2. So what we see is that there's this region of overlap here, not including +2, where all these numbers between these 2 points satisfy both inequalities. The left-hand inequality is true and the right-hand inequality is true. And we can write that as a nice compact inequality by saying -2 is less than x, which is less than or equal to, I have messed this one up. So working from left to right, -2, x is greater than or equal to -2, and less than 2. That's that sandwiched region between those two values and also respecting those boundary conditions, whether it can possibly be equal to or not equal to the boundaries. So just to emphasize that this is the best way to write the solution, when a solution is a bounded section of a number line, you should write the solution as from the most negative, or smallest, we sometimes call that, then x is greater than the most negative, and it's less than the most positive. So it's like you're reading left to right on a number line. Most negative to most positive. Most negative value between the most positive value. And obviously, if you're allowed to be equal to that value, then we'd put equal signs there, depending on the situation. I want to show you two more examples where the results of this compound inequality interact in different ways. So in that last example, the two solution regions overlapped in a nice little way where they sort of each contributed these endpoints of the overlapping. Well, now let's look at an example which will have a slightly different result. So to start with, in blue here, I will work on this first inequality. So I'll multiply that 3 into the brackets. So that's 6x plus 15 is less than or equal to 18. And then in, let's use orange, I will work on that second inequality. 2x minus 2 times 7 is 14 is less than negative 6. So I'll solve this light blue one first over on the left. Subtracting 15, I get 6x is less than or equal to 3, which means that x divided by 6, x is less than 3 over 6, which we could simplify to less than or equal to 1/2. In the orange, we're going to add 14 to each side. So I get that 2x is less than negative 6 plus 14 is 8. So that would be that divided by 2, x is less than 8 over 2 is 4. So here we have two solutions, and I'm going to put them on a common number line because it's really, it's tricky to see where these two solutions overlap, especially at first as we're getting new to looking at how these solutions interact with each other. So where do these two regions overlap so that we can find out where they are both true? Because that's that key, right? The word joining these is and. Both inequalities have to be true. So on this number line, I will put 1/2 on there, and I will also put 4 on there. So that means that 0 is over here somewhere. And let's see how these two inequalities interact. So starting with the 1/2, we know that it is all the values to the left of 1/2, x is less than or equal to 1/2. And then going over to the orange one, we have that x is less than 4. So to the left of 4, and I'll do it just above the number line so we can see where these two regions overlap. Well, we need the region where both of these things is true. Now, obviously, if we pick something between 1/2 and 4, like say 3, that's only true, it only lies in the solution region for the orange solution region, or the orange inequality. And it doesn't apply for that other inequality on the left. So the only region where both are true is this region here, which covers both of those inequalities. But if we write that region, the answer is x is less than or equal to 1/2. That satisfies both. So really, this x is less than or equal to 1/2 actually that was the solution to the compound inequality, because it's contained within the entire x is less than 4 inequality. So if both have to be true, we can really only go up to the 1/2 point where that inequality cuts off. So it's just an example of how one inequality basically dominates the other. All this other stuff that the other inequality adds after 1/2 and up to 4, it doesn't matter because it doesn't get satisfied by that first inequality. So it's just the solution x is less than or equal to 1/2. And now here's one more example where we're going to see a different type of solution based on how those two compound inequalities interact. So to start with the one on the left, 1/3 x minus 4 is greater than or equal to -2. So we add 4. 1/3 x is greater than or equal to +2 times by 3 on each side. So we get x is greater than or equal to 6. Great. Now let's move over to this left hand, to the inequality on the right. So that has to be true, and this other inequality has to be true. So multiply that negative 2 in, we get negative 2x plus 6, negative 2 times negative 3, is greater than or equal to 4. We subtract 6 from each side, so we have negative 2x is greater than or equal to negative 2. Then we divide each side by negative 2, and we have to be careful because we're dividing by negative 2, which means we have to flip this inequality. So we have x is less than or equal to negative 2 divided by negative 2 is positive 1. So these two inequalities both have to be true. They are joined by and. So let's see what that looks like on the number line. So our two numbers of interest are 1 and 6. And if we go ahead and graph these two inequalities, so x is greater than or equal to 6 is over here. This would be the light blue inequality. It's heading off to the right. And then the other inequality in orange, x is less than or equal to 1. So fill in the dot and head to the left of 1. Well, what is the region where both of these inequalities are true? Can you see it? There is none. There is no solution. There is no x value or values that satisfy both of these two inequalities. And that and is very important because it says both this inequality and the other must be true. That's what and means, one and the other. So there is no solution. That is our answer to this compound inequality. No solution. So if there isn't a region that satisfies both of the two inequalities, we say no solution, and that's a type of result you should expect in some of these compound inequality problems.